Hello, and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy them. So check out Linode. With 200 gigabit private networking, scalable shared block storage, and a 40 gigabit public network, you've got everything you need to run a fast, reliable, and bulletproof data platform. If you need global distribution, they've got that covered too, with worldwide data centers, including new ones in Toronto and Mumbai. Go to dataengineeringpodcast.com/Linode today to get a $20 credit and launch a new server in under a minute. And go to dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, read the show notes, and get in touch. And don't forget to go to dataengineeringpodcast.com/chat to join the community and keep the conversation going. Your host is Tobias Macy, and today I'm interviewing Tom Kaitchuk about Pravega, an open source data storage platform optimized for persistent streams. So Tom, could you start by introducing yourself?
Yeah. So I've been working on streaming systems for basically my entire career. I sort of inadvertently started out in this by joining Amazon as an intern, and subsequently worked there for 7 years. And I started on a team that was called Distributed Systems Engineering at the time, but eventually it became known as Amazon Web Services. And I did the backend for the second version of SQS and the simple workflow service, which ended up not being quite as popular externally, but is very widely used within a lot of the other services as internal infrastructure component. And I ended up under a manager there who then went to Microsoft and was working at Azure. And he called me several years after he left, and I was working at Google at the time. And he pitched, we need to create this product, and he described the need for a log storage system and why it was essential. And essentially, he joined EMC at the time and convinced them to spin up a team to build this sort of infrastructure. And he brought me aboard, as well as Flavio Junqueira, who's famous for Zookeeper and Bookkeeper. And we put together a team and built it from there. So that's sort of how we got into it. There's a lot of details behind it, but the core advantage of Pravega is that it treats data as a stream and is itself a streaming platform. So that's sort of where everything else follows from that one key idea.
Yeah, and if you just glance at it very quickly, in some ways it looks similar to platforms such as Kafka or Pulsar that are a sort of persistent log system. But as you get a little closer and look through the other capabilities, it becomes obvious that there are a lot more capabilities and options and use cases that Pravega enables. So I'm wondering if you can discuss some of the main types of workloads that it was originally designed for and some of the primary ways that people are using it.
So the biggest thing that is sort of distinctive about Pravega as opposed to Kafka and Pulsar is that it's sort of managing your archival storage natively. So Pravega divides things into sort of tier 1 and tier 2, and this is sort of a common pattern that you see with people using Kafka, Pulsar, etc., where you'll stream some data in, and it'll be on that system for a little bit, and then a retention period will kick in, and it will drop it, and you'll need to have some process that's spooling that data and dumping it into HDFS or something like that, or S3 or whatever. So Pravega's managing that internally, and the reason it's doing that is because that's actually part of the architecture. It's not sort of some secondary thing where it sort of jumps and it's bolted on, that sort of transfers the data out. It actually is designed to hold in sort of a quote unquote infinite storage volume, provided you have disk capacity. It can just continuously stream. It's not separating out your low latency stuff from your high latency stuff. It gives you a common interface for both of those. So that's the first thing that most people see. But the other thing that it does is Pravega gives you strong consistency. And the reason it does that is because it actually is a stream under the covers, right? A lot of times we talk about streams and we say, here's a bunch of messages, and those constitute a stream. But they don't really. They're just a set of discrete messages, and when you start getting down into it, they can be reordered, and they can be duplicated, and so forth and so on. On the Pravega server, all data is contiguously treated as a contiguous string of bytes. It doesn't actually know where one event begins and the next ends. So there's no such thing as duplication or reordering, because from Pravega's point of view, those are tantamount to corruption, because it can't tell where one begins and another ends, so it can't possibly duplicate. The other thing that comes directly from having strong consistency is that you can build up more complicated primitives. So the simplest you can do is compare and set operator. You can append data, but have that data be conditional. That I want to append some data to the stream, but conditionally on this metadata value being X, or the length of the stream being Y. So you can do these operations conditionally, and we can build a bunch of APIs on top of that. And one of them that we build that's probably the most widely used version of that is transactions. So what you can do is you can write a bunch of data to a stream and say, I want all of this to go in or none of it. I want it to be atomic. And that is unbounded in the amount of data you can put down there. Because what's actually happening under the covers is that data is being written to a segment. We divide streams into segments. It's written to a segment, and that segment is when you call commit via a metadata operation, conditionally merged into the stream that it's a part of. So you can perform this atomic operation over large volumes of data with very little overhead.
And so you mentioned that the representation of the stream on disk is just this sequence of bytes, and it also has these concepts of segments for being able to adapt to different usage patterns or volumes of data going through the system. So I'm wondering if you can talk a bit more about the actual on-disk representation and some of the benefits that it provides in terms of persisting the stream and how that manifests in some of these higher order capabilities, such as the transactions or exactly once delivery and things like that.
Okay, yeah. So streams are broken into segments, and the reason for that is so that they can scale up or down as needed. So if you can think about a stream as we have multiple interfaces, but when you're dealing with events like you would in Flink or if you're connecting to Flink or Spark or something, you have a bunch of discrete events, and you will send those events to different segments that are all part of the same logical stream. But those segments certain events will need to go to one segment, and certain events will need to go to another. And so the way we manage that is we define a sort of a key space. If you can imagine, like we take a string and we sort of hash it to a floating point between 0 and 1. And then we can divide up that space and say, okay, events that have their keys associated with 0.5 will go to this segment, and 0.75 will go to this other segment. That also gives us a continuity. So across time, if we can change the number of segments, but you can imagine, like for any given key, there's a contiguous order of what segments they should go to. And so as long as you read them in that same order that they were written to, order is maintained even though the number of actual segments is changing out from underneath you. So a segment might be on one machine, but then it might scale up and split into two and then be split across two machines, et cetera, et cetera. So you can dynamically adjust how much resources a stream has access to by scaling the number of segments. In terms of how the data is laid out within a segment, it's actually very simple. It's when it ends up in tier 2, the data is written, aside from sort of a separate metadata file that's maintained for other reasons, it's maintained as files that just contain the raw data that was written to that stream. There's no framing or overhead or anything. Depending upon your tier 2 implementation, which, like say you're in HDFS, for example, it might be split up into multiple files, but they're just contiguous and one follows right after the other.
And in terms of the way that the segmentation happens for adapting to the usage patterns, I know that looking through the documentation, it mentions that it will use different sort of time allocations and split one stream into multiples in the event that there are more consumers than can be supported with just one stream, or if you have more writers and less consumers, it will recombine the different streams. So how does that logic function in terms of determining what the sort of transition points are and any tuning capabilities that are available to operators or application developers?
For each stream, there's a configuration file, and that configuration specifies we call scaling policy. The scaling policy contains like a target rate that you want to have on a per segment basis, and that can be defined in terms of sort of kilobytes per second, or it can be defined in terms of discrete events if your stream is defined in terms of event.
And for the automatic tiering of the storage subsystem, that's one of the other things that seems very compelling about Pravega is because you have that single API for data that is both on cluster and life cycled out to some other storage mechanism. I'm wondering if you can talk through some of the challenges of providing that unification and any routines that you do to try and hide some of the latency issues of fetching that data back, and any of the types of lifecycle policies that are available to operators.
When data comes into Pravega, it's written to what we call tier 1, which is a high speed, low append latency storage system. It's notable that it's never read from there, and if it was, that would incur very significant costs. So it's a very key to the architecture that we don't read from the tier 1 storage unless we're doing recovery from a host failure. So data is written to tier 1. Once it has been written and enough data has accumulated for a given segment, that data is then written as a large block to tier 2. And usually that takes the form of an append, where it's appending onto an existing file. Now, this means that when a read comes in, the data may or may not be in tier 2. If it's not in tier 2, it has to be served from Pravega. When the data is in Pravega, we need to be able to serve reads to it. But the data may or may not be in tier 2. If the data is not in tier 2, we have to serve it out of Pravega's local storage. That is a RocksDB that is configured to prefer to stay in RAM, but if it has to, it will spill to disk. And notably, it has its journaling turned off. The reason for that is because we're using the tier 1 storage for durability. So we can read data out of Pravega's cache here that's in this RocksDB and serve read requests there. But obviously, the majority of read requests won't be able to be served out of the cache because the cache is inherently small. What we can do is we can have a read request go to tier 2, pull in a large amount of data, more than the user needs, and then return extra data or hold it in memory, waiting for the next read call. The advantage of this in the streaming architecture is that the reads are incredibly predictable. By doing this simple read-ahead optimization, we can effectively reduce the latency of the reader to 0, because we always have the data in RAM ready to go by the time they issue the next request.
And when you're performing requests to the tier 2 storage to retrieve a particular block, and you mentioned that when it is persisted to that tier 2, it's often written as an append operation. So I'm wondering if there's any complexity or resource limitations that are imposed by having to perform seeks from the beginning of a given file if you have large chunks, or how that is managed in terms of being able to fetch the different segments. I was just assuming that when it's persisted to tier 2, since you're creating an append operation, I'm envisioning it as being all in a single file rather than maybe a series of contiguous files. So I'm just wondering, in terms of the actual representation within that storage medium, if there's a need to open a given file and then seek to a particular location to retrieve a specific segment, or just how that overall operation is manifested.
So in tier 2, there's at least one file per segment. So you don't need to move around to look at more than one segment. You can just read contiguously, and all the data in the segment, and all the data in the file corresponds to the same segment and is contiguous. So there's no processing that's needed. But some tier 2 implementations don't support append operations, or an append operation involves reading the old data and then concatenating it with the new data and then writing it back. For those tier 2 implementations, we simply don't do an append. We simply create a new file, write the new data there, and then name the files in order such that if you read one and then the next and the next and the next, it gives you the all of the data in order.
And another question that I have that's not necessarily specifically relevant to the storage tiering, but more in terms of the representation of the stream, is if you're trying to seek to a particular point in time, for instance, if you're retrieving discrete events, if there's any sort of metadata that gets stored for being able to identify at what point in a stream or where in a segment you would need to move a pointer to be able to read a specified set of events or a specified time frame.
Yeah, that's actually a good question. So, as I said, the server doesn't understand where event boundaries are. So, it can't help you locate the beginning of an event, for instance, or it can't help you seek randomly. So, the way that's implemented is we have this concept called stream cuts. So, at any time you can call an API to grab a stream cut, and you can do this from the writer or from the reader, and that will represent the current position in the stream. So, on the writer side, it's where data would be written right now if you're going to write data. And from the reader side, it's where your readers are at the current moment. And then you can, in the future, jump to a particular stream cut. So you can start a group of readers and say, we're going to start reading it at this stream cut and provide it. So that lets you define things in terms of boundaries that are meaningful to the application.
And so for somebody who is building an application on top of Pravega, I'm wondering if you can talk through a bit more of the interfaces that are available and some of the architectural or design patterns that would work well for building something on top of Pravega as its own streaming engine.
Yes. So we have several topic level interfaces. The one we've sort of been talking most about is the event oriented ones. We have an event reader and event writer that lets you stream a sequence of events, and you can define their format and so on. But they're in discrete units and scale up and down. There's others. For instance, there's the simplest is a byte stream writer, which gives you a sort of a Java input stream and a Java output stream, and you can treat it as a contiguous stream of bytes. Obviously, being a byte output stream, having multiple writers at the same time doesn't make sense, because how would the data be interleaved? Like, there's no clear, like if you randomly shuffled the bytes into each other, it wouldn't make sense. But you can use it in that way if you have a single endpoint on each side. So that's useful for some applications. Another API we have is called a revision stream client. And this is a very low level API that probably most applications won't use, but ends up getting used in a lot of sort of infrastructure components that want to write more sophisticated APIs on top of it. So the way it works is it takes in, blobs that can be written, and you write any number of them, and at any time you can conditionally add a new one based on a version number. So essentially there's a version number that gets incremented every time you add one of these things, and you can add another one conditionally. And the main use case for that API is actually a higher level API that we surface called state synchronizer. And state synchronizer has an interesting model. If you have an application and that application has an in-memory object, and you want that in-memory object to be, sort of replicated identically across your fleet, but also make updates at the same time, you would use state synchronizer. And so the way that works is you define a class for each type of update that can be applied to your state object, then define a serialization function for each of those update objects. So you define your serialization function, and all the updates that you apply are applied conditionally using the revision stream client API, so that they're conditional upon you having received all of the previous updates. And once those new updates go in, you get an acknowledgement back and you apply them locally. So this guarantees that all the instances of the application that are using the same state synchronizer will receive all the same updates in the same order. And assuming your update function is deterministic, will give you the same in-memory object. So you can use this to, for instance, synchronize config files or schemas or things like that are relatively low update frequency, but very important that they be consistent across your fleet.
And so I know that when I was looking through the documentation, it mentions that Pravega is useful for things like leader election and, as you mentioned, configuration updates. But I'm interested in what you were just saying about being able to use it for storing schema records, particularly given that there are systems such as I forget the specific name for it, but the schema service built on top of Kafka by the Confluent folks, and I believe that Pulsar has a similar capability. So is that something that you could use in Pravega as well, as far as using the state synchronization for updating maybe an Avro schema to ensure that it is conformant with any events that are being written to a given stream?
Yeah, so the pattern there would be you have some stream and you have a schema associated with it, and that schema is going to change over time. What you would do is you would take a stream cut and say, this is a point in time that I'm defining. And then you could associate that stream cut and say, before this stream cut, the schema was X, and after the stream cut, the schema was Y. And for all the hosts that need to know that information, there's many of them and they're distributed. So a good way to do that would be to put that information in a state synchronizer, and then everyone will have access to it. And any updates that you make to that mapping will be observed by all of the hosts.
That right there is Just thinking through it, that sounds like one of the most amazing things I've heard in a long time as far as how to build a system and ensure that you have consistency in terms of the schema representation as it evolves over time.
Yeah.
Because I know that for various systems, there are different schema representations, but particularly for things like Avro or Parquet, where the schema is inherent to the record, but it can change as you're going through time, and needing to be able to have clients that can intuit that fact and process the events, particularly if you're trying to do a full replay and rebuild a data warehouse, maybe from, point zero in time, having that schema association directly associated with the transition points at which it changes and evolves, I imagine would greatly simplify the overall logic of the processing system.
Yeah. Yeah.
And so with all of that, I'm wondering if you can dig a bit more into the overall system architecture of how Pravega is built, and particularly when you're deploying it in a production environment with multiple instances in the cluster, how that cluster manifests and how the architecture plays out within the fleet of servers.
So Pravega's architecture is a bit interesting in that its client is thicker than people are used to. Most services have a very thin client and are easy to churn out new client APIs and new languages, which is definitely an advantage. Pravega does not have that advantage. And the reason is because it has the server does not have a deep understanding of the data. The server is dealing with contiguous streams of bytes. So it's up to the client to impose everything on top of that in terms of, if you want to deal with versions, if you want to deal with events and serialization and formats and, scaling, all of that is done in the client. So the client's actually fairly sophisticated. The way that the client works is there's a process we call the controller, which is essentially a metadata and discovery service that tells the client for any given stream and segment of that stream where it needs to connect. And the servers coordinate to manage ownership of segments. So there's only one server that has ownership of any given segment at a time. And the client then directly connects to the appropriate server and starts sending data. So then if you want to, for example, scale a stream, what ends up happening is that the controller's monitoring the rate of traffic on the stream. And if it decides that more segments are needed, it will send a notification to the servers to create new segments, and we call seal the old segment. So new segments will be created, and anyone attempting to write to any of the old segments will get an error. And the client will interpret that error and say, hey, that means something, that the scaling event has occurred. And we'll ask the controller, what are the new segments, and then locate them and connect to the appropriate server. So which servers are involved in a stream can change dynamically over time. And the client is connecting to them directly without going through some sort of proxy that's hiding the fact that there are multiple servers there. This is somewhat of a challenge in certain deployment environments because a lot of times people want to deploy a service and put it behind a VIP and sort of say, okay, well, there's only one endpoint, but that doesn't work with Pravega. It needs to be able to uniquely address the client needs to be able to uniquely address each of the servers.
And so in terms of scaling the number of servers up or down, the client would then need to be updated with the configuration for those new instances, or is there some sort of gossip protocol that can allow it to pick up that new information from the cluster itself?
It would find that out from the controller. So what would happen is you could add new hosts to the system, and initially they wouldn't have any traffic going to them because nothing was assigned. But then the controller might take some action to sort of reassign some data from the existing host to the new host. And when that happens, any client that was connecting to the established host that lost that segment that they were attempting to read or write to would receive an error, and the client would go to the controller and say, where is the segment located now? And it would receive the IP of this new server and connect to it. So it would happen automatically. The client does not need to be aware of any of the servers. As long as the client is aware of at least one controller, it should be able to discover everything else.
And in terms of the resources for the servers themselves, particularly the storage layer, since the tier 1 is essentially a temporary store that's primarily just for being able to rebuild state, does that mean that there's not really any need to linearly grow the amount of storage as the cluster is in use for a longer period of time, and you would just need to worry about that at the tier 2 layer?
Correct.
And then one of the other use cases for Pravega that I was seeing in the documentation is for using it in conjunction with other streaming engines such as Flink, and I believe that there might be some plans for other engines such as Spark or Heron, things like that. So I'm curious, one, the use cases where you would want to use an additional streaming engine on top of Pravega, and what's involved in adding support for Pravega to those different engines.
Yeah, so we definitely work very closely with Flink. They're sort of the stream processing platform we've spent the most time with and coordinated with very closely. And the reason why you'd want to use Pravega and something like Flink is that, Pravega stores your data, and it can scale up and down and do all of those sorts of things, but it can't provide you any sort of data processing capability. It doesn't give you the ability to query things or the ability to aggregate data and perform computation on it, which Flink is ideally suited for. And Flink actually doesn't natively have any storage capability. So it's sort of a perfect match, right? If you combine Flink and Pravega, you get all the advantages of Pravega storage, but then you have Flink's ability to perform things like SQL queries on top of it, and you don't have to sort of think about how you would engineer that, on a Pravega stream. And the story is similar for Spark or Heron. Certainly, Flink is the most mature connector for Pravega. It's hosted in our repo and has by far the most usage.
And then in terms of the actual semantics of the stream itself, I know that exactly once is sort of the holy grail in these types of systems and can often be difficult to achieve. And Pravega advertises support for the exactly once semantics. And you also mentioned earlier the transactional capabilities. So can you talk a bit more about how the exactly once semantics are manifested in terms of the way that the streams are represented, and some of the ways that transactions can be beneficial when combined with something like Flink for doing the stream analysis?
Yeah, sure. So Pravega actually offers a stronger guarantee in terms of exactly once than almost anything out there. And the reason is precisely because of transactional support. So a lot of systems are able to do exactly once processing, assuming you get the data into their system exactly once. And then, once that occurs, it will be processed once, assuming that the processor follows the appropriate protocol. Pravega can actually do better in that it can guarantee that you can get the data in exactly once because it has a transaction. So what this means is you can write data in a transaction, call commit, and then all that data is made available to the data processor. The data processor can process it, and if it fails, you need to resume from the last point where it produced output. Now, in a conventional system, that's very hard to determine. But if the point that it's produced output is determined by a transaction, because, for example, you're connecting and writing your data out to Pravega, then you know the point at which the transaction committed. And so what you can do is you can restart from exactly that point where your output has been persisted. And the way that you do that is when you are reading data, it's handing you a marker that we call position. And that position object corresponds to the location in the stream. So when a host dies, you can reinstantiate it and say, okay, it's going to resume from this position and provide the position object. So this allows you to do something where you have, like, say, a Flink job that is processing data, doing some complicated aggregation, sending it into a Pravega stream, having it go to a different Flink cluster and run a different job on it, and have that all the way end to end exactly once. In the absence of a transaction, there would be no way to do that, because the data would be emitted by the first Flink instance and then be partially emitted and then crash. And so it needs to resume from its Flink needs to resume from its previous checkpoint, but it already emitted some of the data. So what you would need to do is you'd need to undo those sends. But the only way to do that is to have not really sent them, and to have a transaction and not have committed the transaction yet. So by having transactions, we can do end-to-end guarantees across multiple processing steps.
And in terms of handling out of order events, which is another big challenge in systems that are processing unbounded streams of data, would the transactional capabilities and the segmenting of the streams give you some avenue for being able to handle some of that out of order capacity for certain time boundaries?
So it's not really. So the way Pravega handles order is the server itself is always going to guarantee order. The server itself doesn't understand what events are, and so everything that goes in there is going to come out in the exact same order. But that's only true on a per segment basis. As soon as you talk about having multiple segments and things scaling up and down and the number of segments changing, the story gets more complicated. And so the way that we do that, and the way that we allow you to have order guarantees when you have many segments and the number of segments is scaling dynamically, is when you write any given event, it has associated with it we call a routing key. And that routing key determines the number of routing keys you have determine how much parallelism the system could have. So a given routing key cannot be split across multiple readers in a reader group. You can have many routing keys and have the different routing keys end up on different readers, but a given routing key will not have its traffic subdivided. So that gives us a clear way to define a notion of ordering, which is that we say all events for a given routing key are ordered with respect to other events with the same routing key. And we can scale up and down, but for any given routing key, we hash that routing key into a key space. And that key space is a contiguous sequence of segments that are responsible for it. And so as long as you read those same segments in the same order, you get that guarantee.
And going back to the operational characteristics and also in terms of application design or system design, what are some of the edge cases that users and engineers should be aware of?
So there's two. One is the one I sort of already mentioned, which is the client is thick and needs to be able to address each of the servers, the Pravega servers, directly. So the client needs to be able to directly connect to each of them. So there can't be some sort of firewall that's only allowing like one endpoint to in between the client and the server. The other thing that is a little bit tricky is that a lot of the containerization systems very naively don't expect that you really store things on disk, or that you do and that they're not important. But since Pravega is storing data until the data ends up in tier 2, that data is stored on disks that are necessary for replication. You need to make sure that you don't configure a policy whereby the framework will simply restart or wipe multiple of the storage servers at the same time. So any sort of upgrade that's going to replace disks needs to be done on a very granulated basis, whereby re-replication has time to occur in between.
And in terms of your overall experience of building and working on Pravega, what have you found to be some of the most interesting or useful or challenging lessons that you've learned in the process?
I've learned things are harder than I thought. Probably the thing that complicated things most in terms of Pravega's architecture is scaling. It touches everything. You can't do any additional feature without interacting with scaling like immediately. So you're always sort of thinking about that. The other thing that I think that was sort of an experiment, honestly, for us, was I came up with very early on in the project a set of thread safety guidelines that said we're going to follow these everywhere. And of course, Pravega being very multi-threaded code, we wanted to make sure we didn't have race conditions. So we hammered out a set of guidelines that said, this is how multi-threading should be done. And it's very explicit about it. And those had to be modified a little bit along the way, but they've really worked out, and they've prevented a tremendous amount of bugs. So I'm very pleased with the way that turned out.
And what are some of the cases where you would recommend against somebody using Pravega for a stream-oriented system?
Anytime you're going to need to perform a lot of like random seeks or reads, Pravega has very good latency on write because it's writing to an uncontended disk, and it has very good latency on read because you're reading from prefetched data. But the latency of a random read that is not one that can be mitigated by prefetching it because it's not sequential is going to be essentially whatever your tier 2's read latency is. And most implementations such as HDFS and S3, that's quite significant. So if your architecture requires that you do any significant number of points where you jump around or you reread a particular event in sort of a random time after you initially read it, that doesn't make sense. That should be offloaded to a different system.
And one other topic that we didn't touch on yet is because of the fact that you have this capacity for unbounded storage of your stream for the entire history because of that automatic tiering, it in some cases can remove the necessity to have multiple processing systems to do both short-term and long-term analysis of the data, as is commonly built with something like the Lambda architecture. So I don't know if you want to talk a bit about that and some of the design patterns that Pravega enables to replace those system characteristics.
Yes, that's exactly right. So from our perspective, Lambda architecture is sort of a dirty word. We prefer what's becoming known as the Kappa architecture, where the streaming system sort of subsumes the archival storage, not because you're not using archival storage. You are. You're still erasure coding and using cold storage and stuff like so on. But you're using the same interface to access the data that's in that system as you are for the new data. So you don't have to rewrite your processing logic twice, and you don't have to worry about trying to sync them up. I've gone to multiple Flink Forward conferences, and every year there's somebody who's described just how difficult of a problem it was for them to coordinate doing a backfill job where they transition from working off an archive to working off live streaming data, and managing that handoff between the two systems and getting it right so that events aren't missed or skipped in between. That can be very difficult to engineer. So it's better to simply avoid having to write your logic twice and managing that handoff by having a common interface to both your cold and your hot data, and then you can just use a common set of processing logic and work continuously from the beginning of time until present.
What do you have planned for the future of Pravega?
One feature we're working on that would probably make a big difference to a lot of customers is watermarking. So we're basing our design on watermarking on Flink's model, where the writers supply a particular point in time mark, a time mark when they are writing the data initially, and the readers can see these marks when they're reading the data. And in particular, they can get an upper bound. They can get the information that all writers, when they were at this point in the stream, produced a timestamp that was at least X. So you can guarantee that you won't see events from below X in the future.
And are there any other aspects of Pravega or stream architectures that we didn't discuss yet, which you think we should cover?
So Pravega has capability in its wire protocol that really reduces latency on append. And what it does is it sends a header effectively that says, okay, the next following bytes are going to be an append to such and such segment. And then the client can start appending bytes. But that it actually sends the header before it actually has all of the data or has a large amount of data. So what this allows the client to do is to just immediately start writing data, because it knows that it's a streaming system, right? There's more data coming. It's a continuous stream of data, so of course there'll be more. So it just goes ahead and writes the header and starts writing data, and the data is already over the wire and down to the storage layer by the time the end of the data comes, and the client says, okay, and that's the last of it, and it closes out that block, as it were. So that lowers latency because the data is already transferred before the final bits are sent. And the way that works, essentially the client tells the server in advance, here's how much data I'm going to write, and then following that, there'll be another header. And following that, there'll be a header saying, oh, and here was the actual length of the data, and there might be additional bytes. And the server will take all of that data and append it atomically, because all writes in Pravega are atomic.
All right. Is there anything else that we should touch on before we close out the show?
You mentioned leader election. I could talk about that if you want.
Yeah, sure. Let's talk about the leader election capabilities and how it compares to some of the synchronization and locking primitives that are available in things like Zookeeper, which I know you also build on top of.
So Zookeeper has sort of inherent scaling limitations, right? Both in terms of the amount of data stored and rates. But the thing that it provides that's very powerful is consistency. So Bookkeeper, in turn, uses Zookeeper's consistency to provide what they call write fencing, where if one server is writing and another server wants to take over, they simply write some additional data there, and then the first server's writes will fail. Pravega follows a similar model, where the controller manages which server is responsible for which data, and that mapping is written in Zookeeper, but the actual handoff, the consistency is maintained by fencing. And the way that works is the new server that's taking over a particular segment will simply close the record in tier 1, and then it will create a new one. So the first server can't succeed in doing any writes. So what this allows us to do is have consistency all the way up at the application level, where we can make sure our pens are atomic and make sure that even in the event of network partitions or multiple hosts coming in and out, that we will have a consistent set of values that are written to a stream. And State Synchronizer obviously uses this to achieve its consistency, but it can also be used to do other things. And one of the things that we have as a sample that we put up on our GitHub is a leader election. It is a leader election algorithm. So a bunch of hosts all will go to Pravega and write some data, and one of them will win because you can do compare and set operations, right? And then that one can become the leader, and at that point you can have things like heartbeat mechanisms which update, which write data regularly, and if a heartbeat does not occur, some other host can write that it's declaring the first host dead and is taking over for itself, for instance. But the first host can't succeed in heartbeating if that data has been written, because the heartbeats can be conditional upon it having seen all of the data in the stream, and so it will obviously not attempt to heartbeat if it has seen that it has been declared dead. So you can use that mechanism to maintain a leader election capability.
That's an interesting approach to that problem, because most of the systems that I've seen that have some form of leader election require a quorum vote to establish which instance is the leader and ensure that there are enough instances available to perform that election. And so that also raises the question of how that manifests as far as both Pravega and systems built on top of it being able to make certain trade-offs along the axes of the cap theorem.
Right. So in terms of cap theorem, Pravega chooses consistency. And that doesn't mean that availability is necessarily bad. It's the same as it would be in most other systems, where if you are on the side, in many systems, if you're on the majority side of the network partition, then you can continue working and the minority can't. Pravega is somewhat similar in that if you're on the side, if you're reading and writing from a particular segment, if you're on the side of the network partition that owns that segment, then you can continue working. And if you're not, then you can't. And the ownership of the segment is similarly maintained by the controller, and that's ultimately, that map is in Zookeeper. So that map might be updated, but it can only be updated on the majority side.
That's interesting. Yeah, it's funny how often people consider the cap theorem as being very sort of binary or trinary in terms of which axes it supports, but it's much more of a gradient along the different axes of the consistency, availability, and partition tolerance, it's always interesting to discuss the ways that systems make those trade-offs.
Yeah, definitely. And I think, there's a lot you can do in terms of, a lot of people sort of give up and say, oh, well, we're choosing consistency or we're choosing availability, and completely give up on the other. But even if you're not willing to make any sacrifices on one, you can usually make a fair amount of headway on the other.
All right. Well, for anybody who wants to follow along with the work that you're doing or get in touch, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
Interesting. Yeah, I think the biggest gap is actually on ingest. So there's very good stream processing capabilities with things like Flink. I think Pravega is showing that there's very good storage capabilities, and certainly persistent systems like object stores are very mature in themselves. But ingest is actually very immature and is very fragmented. There's many different systems that all work very differently, and they haven't even yet gotten to the point where there are consistent patterns that are sort of universally applied. So I think that's the area that is lacking.
All right. Well, thank you very much for taking the time today to join me and discuss the work you've been doing on Pravega. It's definitely a very interesting project and one that I am excited to see how it progresses into the future. And as new streaming engines add capacity for it, I'm sure it'll have some transformative effects. So thank you for that, and I hope you enjoy the rest of your day.
Thank you very much.